Okay, so now we're going to look at multiplying and dividing functions. So pretty much same idea as yesterday, except for now we're going to multiply and divide. All right, we'll start with multiplying and dividing functions and looking at those equations. So first of all, it says determine h at x equals f at x g of x. So I'm just going to show you something. So h at x equals f at x g of x. Sometimes you'll see the multiplication written like this. Sometimes you'll also see it written like this. So you'll see a closed dot that's circled in. You do need to pay attention to that dot being circled in. And next lesson, tomorrow, we'll look at compositions where the dot's not circled in, so you do need to pay attention to that. Okay, so let's start off by multiplying these two functions. So we have f at x, which is 2x minus 1, times g of x, which is 3x plus 4. Again, make sure you have the notations. You should have that h at x. You should have the equal sign in each and every single step. You don't just make the equal sign disappear. So you're going to go ahead, you can distribute, use the FOIL method, whatever you feel more comfortable with. I'm going to end up with 6x squared plus 5x minus 4, though, after I FOIL this all out. Okay, so that should be a plus sign. So if you were to graph this, you end up with a quadratic, and I can graph it really quickly with you here. So I'm going to go ahead and graph y equals 6x squared plus 5x minus 4. And now I always show this to kids as well. Math 30-1 is always the best. The students that do the best find multiple ways to do each question. Just to verify. So I'm going to write this equation in factored form. And the reason I'm doing that is they should end up giving me the same graph, as long as I didn't make any mistakes when I was FOILing and collecting like terms. And you can see there on your calculator, they do give you the same graph. So this is a quadratic graph, meaning the domain will be x is an element of all real numbers. However, my range, I'm going to need to find that minimum point. So that I find the lowest point of this graph, I'll choose minimum. Left bound, I'll move to the left. Right bound, I'll move to the right. Okay, and I end up with a minimum point with a range of about -5. So when we go back to our PowerPoint, we know the y value, the lowest it goes, is -5. So then my domain for this function, this time I'm going to write in set notation, is x is any real number. But the range for the function for all y values, y would be greater than or equal to -5, where y is an element of all real numbers. Once again, make sure you're very particular when you're writing out your notation. So now what we're going to do is we're going to divide these functions. So k of x equals f at x divided by g of x. So now I'm dividing the functions. Okay, you can actually find your vertical asymptote. We covered this in Math 20-1 by trying to figure out what would make that denominator equal to 0. So if just by looking at it you weren't sure, you could always just write 3x plus 4 can't equal 0, right? Because we know we can't divide by 0. So we're looking for what x value would give us a denominator of 0. So algebraically I can move the -4 over and then divide by 3. So that means my vertical asymptote will be x cannot equal -4 over 3. So when I write my domain, I have to include that asymptote. So for all x values, let's try that again. X is any real number, however, x cannot equal -4 over 3. And we're not going to worry about the range. There is actually a horizontal asymptote as well as a vertical asymptote, but we won't cover this until a later unit. So just like with adding and subtracting, we talked about how you can add or subtract functions given their equations, given graphs, given a table of values. The same is true with multiplying and dividing. So we're just going to look at two graphs here this time. So for A, I'm going to start with A. Remember that -2 shows you the x value. So another way I could write this would be like this. F at -2 times g of -2. Okay, so when x is -2, my f value is +3. When g is at -2, my g value is -1. So really I'm taking 3 times -1, which gives me -3. So the value of f times g at -2 is -3. So we can try the same thing for when x is 1. So remember that 1 is the x value. So the f function at 1 is 0. The y value at 1 is 2. 0 times 2 is 0. Anything times 0 is 0. All right, and then we'll try the division one. So let's do c. So at 0, my f function is 0. Oh, sorry, let me fix that. No, it's not. At 0, my f function is -1. And my g function is +1. So I have -1 divided by +1, which gives me -1. And then d is my last example here. So at 1, this time the x is 1. Okay, my f function is 0. My y function is 2. So 0 divided by 2 is 0. Okay, so this is also a diploma question. You also need to draw the graph. So I'm going to start the same way. I'm just going to draw these two graphs on the same grid. Okay, and all I'm going to do is take, for each x value, I'm going to divide f by g. So let's start at 0. So the f function's at 3. The g function is at 0. 3 divided by 0 is an asymptote. You can't divide by 0. So we actually have an asymptote whenever g equals 0. So whenever my g function equals 0, there's going to be an asymptote on my graph. So I know on this graph there's going to be 2 asymptotes here. So there they are. Those are supposed to be dashed lines. They don't really look like them. Okay, so now let's divide the rest. Okay, so I have 3 divided by 1 gives me 3. There's my next dot. 4 divided by 2 gives me 2. 4 divided by 1 gives me 4. So this is how my graph's looking. So what an asymptote means is it means your graph approaches that asymptote towards infinity. So we know on the left-hand side it's going to get closer and closer to that asymptote towards infinity. On the right-hand side, it's going to get closer and closer to that asymptote towards infinity. So this is what our graph is going to look like. So we could find our domain and range from here. Our domain would just be that x is greater than 0 and less than 4, right? It can't equal because of those asymptotes. So I would just say x is greater than 0, less than 4 for all real numbers. And then my range for this graph, y is greater than or equal to 2 because that's the minimum point there, where y is an element of all real numbers. Okay, so we'll look at a couple more examples here. This time they give us f, g, and h, and we're looking to multiply. So let's go ahead and try that out. So all I'm going to do is fill these in. So f at x is x plus 2. H at x is x plus 4. Times g at x is x minus 3. And h at x is x plus 4. So I'm just going to multiply the numerators, and I end up with x squared minus 1x minus 6, and then I'll multiply the denominators. You could also leave this in factored form because the question doesn't really tell you express one way or the other. So I always have kids ask, well, how do I know how to write it? In your questions, it'll clearly state, or else we'll have to accept both answers. Okay, in the next question here, if h at x equals f at x times g of x, and f at x is 2x plus 5, determine g of x. So what they're saying is h at x is 10x squared plus 13x minus 30. You know f at x is 2x plus 5. We don't know g of x. So really what we're doing is we're saying 2x plus 5 times what gives me this trinomial here. So really I know I'm multiplying two binomials. So 2x plus 5. So in order to end up with 10x squared, if I just look at each individual term here, 2x times 5x would give me 10x squared. So I know my first term in this binomial has to be 5x. In order to end up with a negative 30, 5 times negative 6 gives me negative 30. And then you could multiply it out and check that middle term and make sure it works. But my answer should be 5x minus 6. All right, so here's an old diploma question. Given f of x equals x squared minus 7x, g of x equals x minus 2, and 2x squared plus x over x minus 2. Okay, I think we're missing a term there. Oh, this is h of x, sorry. There we go. Determine a simplified equation for j of x. So we have f of x, so j of x equals f of x, which is x squared minus 7x, g of x, which is x minus 2, plus h of x. So all I do is filling in those functions. Now I'm going to go ahead and I notice that these have the same denominators. That makes this question super easy. Because if you remember from rationals in 20-1, when we're adding rational functions, which these two are rational functions, and we have the same common denominator, really all we're doing is collecting like terms in our numerator. So I have x squared plus 2x squared gives me 3x squared. Negative 7x plus x gives me negative 6x, all over that common denominator. So now that I've collected like terms in my numerator, I've noticed that that numerator is factorable. So I'm going to go ahead and factor it. So I can factor 3x out, which gives me x minus 2. And I notice, hey, I can cancel those x minus 2. So that gives me a function of g of x. J of x equals 3x. So now my domain, because this is a linear graph, okay, x would be an element of all real numbers. My range would be y is an element of all real numbers. However, we would have an asymptote here. So y couldn't equal 2. And we'll get into that a little more. But whenever something's on the denominator, it's going to be a non-permissible value. Okay, so we do have a non-permissible value here, which again you covered in 20-1. All right, so consider the functions f of x equals 2x over x minus 1, and g of x equals x over x minus 3. State the domains of f and g. So if we graphed these, okay, we would graph both of these functions, and they should both have a domain of x is any real number. Oh, I'm mixing my x value there. But both of these would have restrictions. They both have non-permissible values. So for my first function, my non-permissible value would be x cannot equal positive 1, because positive 1 would make that denominator equal to 0. For my second one, so I'll just write that neatly down here. Okay, so for my second graph, it'd be x is any real number, but my non-permissible in this case would be x can equal positive 3, because that's what would make the denominator equal to 3. So now we're going to evaluate. Whenever you see evaluate, it means find an answer. So that 3 is in front, and what we're doing, remember that 2, because it's following the f at g, it means we're replacing the x's with 2. So we're going to go ahead and type this in our calculator. So I'm replacing all my x's with 2. Okay, 4 divided by 1 gives me 4. 2 divided by negative 1 gives me negative 2. So if I were to multiply this all out, I should end up with negative 24. So it says, write in an expression in simplest form for f plus g of x, state any restrictions. Okay. So now we're writing for f plus g of x equals 2x over x minus 1 plus x over x minus 3. So this question, you will need to use some background info from 20-1. So we are trying to we're trying to add and we have different denominators. So this time it means I'm going to have to multiply that 2x by x minus 3 in order to get that common denominator. And I'm going to need to times that x by x minus 1. Okay, so then after I do that, I end up with, I'm going to run out of room here, 2x squared minus 6x all over, and I'm just going to leave that denominator in factored form. Plus x squared minus 1x all over that common denominator. So now that I have my common denominator, I'm going to combine like terms in my numerator. 2x squared plus 1x squared gives me 3x squared. So I'm going to erase this so I can write my answer down. So I have 3x squared minus 7x all over x minus 1, x minus 3. And this equals f plus g at x. All right, so that is, and I can't really simplify that any further, so I'm just going to go ahead and leave it like that. Okay, and it says restrictions. Those restrictions, again, would be x can't equal positive 1 and 3. So the same ones that we wrote down for the domain. It says write an expression in simplest form for f over g of x. So when you're dividing, so this time we're dividing two rationals. And I'm going to erase down here so that I have more room and use a different color. So when we're dividing two rationals, remember you end up multiplying the reciprocal of that second rational. So you have 2x over x minus 1 times x minus 3 over x. Now from here, we can cancel like terms. So those x's cancel out, so then I'm just left with 2x minus 3 all over x minus 1. For my restrictions, they'd be anything that was ever in the denominator. So 1 and 3, still restrictions. However, after I multiply and I switch that reciprocal, the x was on the denominator before I canceled it out. So that means 0 is also a restriction in this case. So when you're dividing, make sure you consider all non-permissible values before you flipped the denominator and after. All right, and that's all for today. So again, try some questions and then let me know if you need any help.